The sea came in through a cabin window. Behind that window, a passenger was asleep. 10:40 at night, hundreds of kilometers from the nearest hospital, and the conditions outside were nothing unusual for that stretch of water. One breaking wave, 7 windows gone, one woman dead from the glass. This was the Drake Passage in 2022. The easy answer is that nothing here blocks the wind. The easy answer is backwards. The open water is the calm part. Why does this narrow gap break ships that survive far bigger storms elsewhere? Crews have been finding that out since 1741. Look at a globe and turn it until the southern hemisphere fills your view, and you will notice something that takes a moment to register. Below about 56 degrees south, the land runs out. Africa ended thousands of kilometers to the north. Australia ended to the north. South America comes closer than anything else, tapering down through Patagonia into the shattered archipelago of Tierra del Fuego. And then it stops too, at a headland of dark rock about 420 meters high that the Dutch named Cap Horn in 1616 and the English turned into Cape Horn. South of that headland there is one gap. It runs roughly 800 kilometers, about 500 miles, from Cape Horn down to the South Shetland Islands off the tip of the Antarctic Peninsula. That is the entire distance between two continents. On a map of the Southern Ocean, it looks like a small thing, a pinch between two land masses, the narrowest neck in a band of water that otherwise wraps the entire planet without touching anything. That narrowness is the whole story, and almost nobody who books passage across it understands why. Here is the part people do get right, and it is worth saying clearly before taking it apart. Between roughly 40 and 60 degrees south latitude, the westerly winds circle the Earth with almost nothing in their way. Sailors named those latitude bands generations ago, and the names stuck because they were accurate. The Roaring 40s, the Furious 50s, the Screaming 60s. Wind blowing over water transfers energy into it. The longer that wind blows over an uninterrupted surface, the larger the waves it can build. And the term for that uninterrupted distance is fetch. In the North Atlantic, fetch is limited by the fact that eventually the wind hits Ireland, or Newfoundland, or Iceland. In the Southern Ocean, at those latitudes, the fetch is the circumference of the world. So swell in the Southern Ocean is not built by the storm you can see out the window. It arrives already grown, from storms that were spinning days earlier and thousands of kilometers upstream, and it keeps arriving whether or not the sky above you looks threatening. A ship in the Drake Passage on a calm, bright day can still be rolling through a swell generated by a low-pressure system south of New Zealand. So far, that is the standard explanation, and every word of it holds up. It is also not the reason people die here, because the open, unobstructed part of the Southern Ocean, the part with the infinite fetch, is comparatively well behaved. Swell out there is long. The distance between one crest and the next can be 200 meters or more, and a long swell, even a very large one, lifts a ship and sets it down again. It is uncomfortable. It ruins dinner service. It does not usually break windows or bend steel. Deep ocean swell in the open Southern Ocean is a big, slow, rolling thing, and modern ships are built for it. What happens in the Drake Passage is different, and it happens because of the pinch. Take a body of water that circles the entire planet, moving from west to east, driven by the strongest sustained wind belt on Earth. Now force all of it through a gap 800 kilometers wide. Everything speeds up. Everything compresses. And the seafloor, which most people never think about at all, reaches up into that compressed flow and tears it into chaos. Start with the shape of the place, because the shape sets every constraint that follows. The Drake Passage averages around 3,400 meters deep, and in places drops past 4,800. Those are averages, and averages hide the shape of the place. The floor down there carries ridges, fracture zones, extinct spreading centers, and one feature in particular that runs diagonally across the entire passage like a submarine wall. It is called the Shackleton Fracture Zone, and it runs northwest to southeast from near Cape Horn down toward Elephant Island in the South Shetlands. It is an oceanic transverse ridge, uplifted by compression across the fracture over roughly the last 8 million years, and it rises several hundred to several thousand meters above the surrounding seafloor. Hold that image, because it matters later in a way that will not be obvious yet. There is a ridge sitting directly across the path of the largest current on Earth, in the one place where that current has nowhere else to go. On the surface, none of this is visible. A passenger on the deck of an expedition ship sees gray water, gray sky, and albatrosses working the wave troughs with a wingspan of 3 meters and a technique that looks effortless because it is. The birds are extracting energy from the wind shear between the crest and the trough, which is only possible because the wind here never really stops. The birds are a clue. They are a wind gauge with feathers. Sailors in the Age of Sail understood that, and it is one of the reasons the albatross carried the weight it did in their superstitions and their journals. Below the ship, though, the water is doing something that took oceanographers most of a century to measure properly, and when they finally did measure it properly, they discovered they had been wrong by roughly 30%. Before that, though, there is a stranger fact about this gap, and it reframes everything. The Drake Passage is the reason Antarctica is frozen, not a figure of speech and not a simplification. For most of the age of the dinosaurs and well beyond, Antarctica was not an ice sheet. It was forested. It sat at high latitude. It was cold, in the way a modern subpolar landmass is cold. And it was connected to South America and Australia as part of the supercontinent Gondwana. Warm water from lower latitudes could reach it, circulate around it, and moderate its climate the way the Gulf Stream moderates northwestern Europe today. Then, the connections broke. Australia separated from Antarctica. And, critically, the land bridge between South America and the Antarctic Peninsula opened into a deep-water gateway, which is the gap ships now cross. The commonly cited window for that opening is roughly 34 to 30 million years ago, though the timing is genuinely disputed in the scientific literature. With published estimates ranging considerably wider, and one live argument is whether the Shackleton Fracture Zone itself blocked deep circumpolar flow until as late as the early Miocene. Nobody should state the date as settled, because it is not. What is not disputed is the consequence. Once that gap opened deep enough, water could finally circle Antarctica without obstruction, and the wind belt above it had a continuous track of ocean to push. The Antarctic Circumpolar Current was born. And a current that circles a continent does something specific and brutal. It isolates it. Warm water from the north can no longer reach the coast directly. It gets caught in the eastward flow and carried around instead. Antarctica was cut off from the rest of the world's heat, and it started to freeze, and it has been freezing ever since. Sit with the shape of that for a second. The gap that gives ships their route to Antarctica is the same gap that made Antarctica worth traveling to. The ice that people now pay $10,000 to photograph exists because that passage opened. The thing that draws them south and the thing that endangers them on the way are not two separate features of the region. They are one event, 30 million years old, still running, and the current that event created is not a normal current. Most people's mental model of an ocean current is something like the Gulf Stream, a warm river of water, a few hundred kilometers wide, moving heat northeast across the Atlantic. By any normal standard, the Gulf Stream is an enormous current. The Antarctic Circumpolar Current is in a different category entirely. It is not a surface skin of water. It extends from the surface all the way down to the seafloor, thousands of meters, and it moves as a coherent mass. It is the only current on Earth that goes all the way around the world and closes on itself. There is no coastline anywhere along its path to slow it, deflect it, or drain its energy. Oceanographers measure current transport in a unit called the Sverdrup. One Sverdrup is 1 million cubic meters of water per second. To put that number in a form a human can hold, the combined discharge of every river on the planet, all of them together, running into all the oceans, is roughly 1 Sverdrup. For decades, the accepted figure for the Antarctic circumpolar current's transport through the Drake Passage sat around 134 Sverdrups. That number came out of measurement campaigns in the 1970s. It went into textbooks, and it went into the global climate models that the world uses to project what the ocean will do over the next century. It was the benchmark. Everyone used it. It was too low. Between 2007 and 2011, a program called Sea Drake put an array of instruments across the full width of the Drake Passage and left them there. Not a research ship steaming across taking readings on a single transect over a few weeks, which is what most previous estimates were built from. Moorings on the seafloor. Pressure-sensing inverted echo sounders measuring the whole water column from below. Current meters. 4 years of continuous data across the entire gap, top to bottom. In the roughest sustained sea conditions, instruments are routinely asked to survive. When Kathleen Donahue and her colleagues published the analysis in Geophysical Research Letters in 2016, the full-depth transport came out at 173.3 Sverdrups, give or take about 10.7. Roughly 30% higher than the number that had been sitting in the models for 40 years. Not a rounding correction. 173 million cubic meters of water per second forced through a gap 800 kilometers wide, extending from the surface to the seafloor. The reason the older estimates missed it turned out to be the deep component. Earlier work captured the baroclinic part reasonably well, the flow you can infer from temperature and salinity structure. What it undercounted was the barotropic part, the deep, uniform push of the whole column, which the Sea Drake array measured directly at around 45 Sverdrups on its own. That deep push had been partly invisible because nobody had been sitting on the bottom, continuously, for years, to see it. Think about what that means practically. The people whose entire profession is understanding this current were underestimating its raw force by nearly a third, using the best available methods for 4 decades. If the specialists were that far off, consider how much confidence a bridge officer on a schedule ought to have about what the water under his keel is doing on any given night. Now put the current and the wind together, because separately, neither one explains the Drake Passage. The wind blows west to east. The current runs west to east. In the open Southern Ocean, that alignment is part of why things stay relatively orderly. Wind and water are broadly going the same way. Energy transfers into swell, and the swell propagates east in long, regular trains. Then that whole system reaches the constriction. Water does the same thing air does when it is squeezed. It accelerates. A current that might move at 20 or 30 centimeters per second across a wide basin has to speed up substantially to push the same volume through a narrower opening. And surface velocities in the Drake Passage core commonly run considerably faster than that, with jets embedded in the flow moving faster still. The current is not a uniform sheet. It organizes into fronts, narrow ribbons of concentrated velocity, separated by slower water. And those fronts meander. They wander north and south, they pinch off, and they spin up eddies rotating parcels of water tens of kilometers across that carry their own local flow direction with them. So the pinch does its first piece of work here. It takes an orderly current and turns it into a field of moving, rotating, colliding water masses, none of which is visible from the deck of a ship. And then the seafloor gets involved. Remember the Shackleton Fracture Zone, that uplifted ridge running diagonally across the passage. When a current that extends all the way to the seabed hits a wall, standing thousands of meters up off the abyssal plain, something has to give. The water cannot go through it. It goes over it, around it and past its flanks, and in doing so it generates internal waves, turbulence, and vertical mixing at a scale that oceanographers spent years trying to quantify. They finally did it with DIE. Between 2009 and 2012, an international project called the Diapicnal and Isopicnal Mixing Experiment in the Southern Ocean, DIMES, released a chemical tracer at around 1,500 meters depth in the southeast Pacific, upstream of the passage, and then followed it. Ships went back at intervals and sampled the water column to see how far the tracer had spread vertically, which is a direct measurement of how vigorously the ocean is stirring itself. Upstream of the Drake Passage in the open southeast Pacific, the mixing was modest. Downstream in the passage in the Scotia Sea, the vertical mixing was around 20 times stronger, 20-fold over rough topography in the region where the current is forced over ridges. So here is the Drake Passage as a physical object rather than a name on a chart, the largest current on Earth, compressed into the narrowest gap available to it, dragged across a submarine mountain range, converted into a chaotic field of jets, meanders, and eddies, with the strongest wind belt on the planet blowing across the top of it. Now watch what that does to a wave. A wave in deep water is not water traveling forward. The water itself mostly moves in circles, up and forward at the crest, down and back in the trough. What travels is the energy. So a swell arriving in the Drake Passage from a storm 2,000 kilometers upstream is a packet of energy moving through water, and its shape depends on the water it is moving through. Send that energy into a current running the same direction, and the wave stretches. Wavelength increases, the crest flattens out, the face gets gentler. It becomes safer. Send it into a current running the opposite direction, and everything reverses. The wave cannot slow down its energy transport, so instead the front of the wave gets held back while the energy keeps arriving from behind. The crests bunch up. Wavelength shortens, and because the energy has to go somewhere, it goes upward. The wave gets taller and steeper at the same time, and steepness is the number that matters, because a wave face can only reach a certain angle before it stops being a smooth slope and becomes a collapsing wall, a breaking wave, which is a completely different weapon from a large swell. A large non-breaking swell applies force gradually. The ship rises with it. A breaking wave delivers a mass of solid, aerated water moving horizontally at speed, and it does not lift anything. It hits. Marine engineers separate these two loads deliberately because they are not the same problem. Green water impact from a breaking crest can generate pressures on a hull side that a static pressure calculation based on wave height will not predict, and it delivers them in a fraction of a second. Here is the part that should change how you look at every wave height forecast you have ever seen. When a marine forecast says the significant wave height is 5 meters, that number does not mean the biggest wave is 5 meters. Significant wave height is defined as roughly the average height of the highest one-third of waves in a given period. It is a statistical description of a sea state, not a ceiling. In any real sea, individual waves scatter around that figure, and a standard rule of thumb is that over a few hours, you can expect to encounter waves close to twice the significant height, and occasionally more. So a bridge officer reading a forecast of 5 to 6 meters is not being told that nothing larger than 6 meters exists out there. He is being told the middle of a distribution, and the tail of that distribution reaches somewhere he cannot see. Now add the eddy field. Within those rotating parcels of water, local surface flow can oppose the incoming swell, even though the mean current is going east. So the sea state on the chart may be uniform across 100 kilometers of passage. We mean while inside a particular eddy boundary, the waves are being compressed and steepened by a local counter-current that appears on no forecast product any commercial ship receives. The number on the screen is honest. It is also incomplete in a specific, physical, well-understood way. And that is the reversal that runs through this entire story. People keep assuming the Drake Passage is dangerous because the waves are big. The waves are big. But the thing that breaks ships here is not height. It is shape. And shape is set by the interaction of swell with a current field nobody can see, over a seafloor nobody is looking at, in a gap too narrow to let any of it spread out, which raises an uncomfortable question about the people crossing it. If the mechanism is invisible, and the forecast is structurally incapable of showing you the worst of it, how is anyone supposed to know when not to go? Somebody solved that problem a long time ago. They solved it without instruments, without forecasts, and without ever crossing the passage at all. The Yagan, who called themselves Yamana, lived in the islands and channels around Cape Horn. And archaeological work in the region places human occupation there on the order of thousands of years. They were canoe people. They moved through the archipelago in bark canoes. They kept a fire burning on a bed of clay or sand in the bottom of the boat while they traveled. And they lived on shellfish, sea lions, seabirds, fish, and whatever the sea delivered onto the beaches. Further north, in the Patagonian channels, the Kaweskar did something structurally similar in colder, wetter, more broken terrain. When Ferdinand Magellan's expedition passed through in 1520 and saw fires burning along the shore at night, they named the place after them, Tierra del Fuego, Land of Fire. The name has stuck for 5 centuries, and almost nobody remembers that it refers to a heating technology carried in a boat. There is a version of this story that gets told badly, where indigenous survival in a hostile place is described as some kind of mystical harmony, and that version is both condescending and useless. What the Yagan actually had was an observation system. Living your whole life on the water at 55 degrees south teaches you to read specific things. The direction the swell is running against the direction of the wind, which is the earliest visible sign that the sea is about to get confused. The way light behaves on the horizon before weather arrives. Which channels stay workable when the outer coast does not. Where the kelp beds are, because kelp grows on rock, and rock means shallow. And shallow means the swell will steepen there before anywhere else. And the single most important element of that system was the decision not to go. That sounds trivial until you understand what it costs. Deciding not to travel means eating less. It means an injured person does not reach help. It means a planned meeting does not happen. Restraint is only a survival skill if you are permitted to exercise it, and the Yagan were permitted, because nothing external was setting their schedule. Look at what they did not do, because that is the tell. They lived at the edge of the Drake Passage for thousands of years. They had seaworthy boats and the skill to handle them in cold, exposed water. They knew there was something south, because whales and seals and birds came and went in that direction. They did not cross. They worked the protected water. They used the outer coasts when conditions allowed, and they treated the open passage as a place that was not for boats. None of that was a limitation of their technology. It was a correct assessment arrived at without a single instrument, and the entire subsequent history of the Drake Passage is the history of people with better equipment reaching a different conclusion. The Europeans arrived with a different problem to solve. Spain had claimed the Pacific coast of South America and was extracting enormous quantities of silver from it, and the only sea route between the Atlantic and that Pacific coast ran around the bottom of the continent. There was the Strait of Magellan, which is protected but narrow, tortuous, subject to violent local winds funneled down between mountains, and in the age of sail extremely difficult to work through with square-rigged ships that could not sail close to the wind. Or there was the open water south of Tierra del Fuego, which was wide enough to give a ship room to maneuver and hostile enough to destroy it. Francis Drake never deliberately sailed the passage that now carries his name. In 1578, after taking the Golden Hind through the Strait of Magellan, he was driven south by a prolonged gale, far enough to establish that open sea lay below Tierra del Fuego, rather than another continent. The first documented rounding of the Horn itself came in 1616, when the Dutch navigators Willem Schouten and Jacob Lemaire took the Endracht around the bottom and named the headland after Hoorn, the town Schouten came from. From that point on, the geometry of world trade included a specific, unavoidable obstacle. If you wanted to move cargo, silver, wool, grain, guano, or warships between the Atlantic and the Pacific, you went around Cape Horn, and you did it in a place where the wind and the current both ran the wrong way. That last detail deserves more attention than it usually gets. The prevailing westerlies blow west to east. The Antarctic circumpolar current runs west to east. A ship sailing from Europe to the Pacific coast of South America has to go east to west, which means fighting both, in the narrowest and most violent part of the system. Eastbound, around the Horn, was a fast passage. Ships ran with the wind and the current and covered ground at speeds sailing vessels could not achieve anywhere else. Westbound was something else entirely. Westbound was a fight that could last weeks. Ships would beat south and west, get driven back east by a gale, gain ground again, get driven back again. Crews worked frozen rigging in constant spray. Provisions ran down, men got sick. And because the ship was making almost no westward progress, the sickness had time to become the primary danger rather than the weather. Which brings us to a British squadron in the autumn of 1741, and one of the most instructive navigational disasters ever recorded, because nothing about it was caused by bad seamanship. The objective was straightforward, if ambitious. Britain was at war with Spain, and Commodore George Anson was given a squadron and orders to attack Spanish possessions and shipping on the Pacific coast of South America, with the prize being the annual Treasure Galleon that ran between Acapulco and Manila. 6 warships left Portsmouth on the 18th of September, 1740. The Centurion as flagship, along with Gloucester, Severn, Pearl, Wager, and the sloop Trial, with supply vessels alongside, carrying somewhere around 1,900 men. The squadron was already compromised before it left. Manning had been a struggle, and the Admiralty had filled out the crews with invalids and pensioners from Chelsea Hospital, some of them elderly, some of them physically incapable of the work. That was not Anson's decision, and he objected to it. It was the resource that existed. The departure was late in the season, which mattered enormously and was understood at the time to matter. Rounding the Horn westbound in the southern autumn means rounding it into deteriorating conditions with shortening daylight. The alternative was to wait months and lose the strategic surprise the entire operation depended on, in a war where the Spanish were already aware something was being prepared. So they went. Watch for that shape, because it repeats in every incident in this story, in different centuries, with different technology. The departure was reasonable given the pressure. The pressure was real, and the environment did not care about either. By the time the squadron reached the southern tip of the continent in March of 1741, scurvy had established itself aboard. Scurvy in the 18th century was not understood as a vitamin C deficiency. The mechanism would not be pinned down for another 2 centuries, and even James Linn's citrus trial was still years away. What the crews experienced was a disease that made old wounds reopen, teeth loosen, gums rot, and legs swell and blacken, and which took men who were still walking 1 week and killed them the next. It did not respond to any treatment aboard. So the squadron entered the passage in this condition, undermanned in practice, crewed partly by men who should never have been sent, with a disease aboard that was killing people daily, and could only be stopped by reaching land with fresh food. Every hour of delay was now measured in bodies. They entered the passage in early March. What followed was roughly 2 months of weather that the surviving accounts describe in terms that sound like exaggeration until you understand the physics from the last few minutes. Seas that arrived faster than the ships could recover from the previous one. Gales that shifted direction and left a confused cross-running sea with no single pattern to steer against. and squalls of hail and sleet that tore sails apart faster than they could be replaced. The ships took structural damage, rigging carried away. Men working aloft in that motion were thrown from the yards, and in that sea, a man in the water was gone. Below decks, the sick could not be kept dry, because a wooden ship working hard in a heavy sea leaks continuously through her seams, and the space where the scurvy cases lay was cold, wet, and airless. And through all of it, the squadron believed it was making progress west. That belief was based on dead reckoning, which was the only tool available. You know your compass heading. You estimate your speed, historically by streaming a log line with knots tied in it at fixed intervals and counting how many run out against a sand glass. You multiply speed by time, apply it along your heading, correct for leeway as best you can judge it, and plot where you must be. Latitude you can check independently with a noon sight of the sun, and that check is reliable. Longitude you cannot check at all, because determining longitude at sea requires knowing the time at a reference meridian, and no clock existed in 1741 that could keep accurate time aboard a rolling ship. That was the entire longitude problem. Britain had put a prize on solving it in 1714, and it was still unsolved when Anson sailed. Dead reckoning has one specific vulnerability. It assumes the water you are moving through is not itself moving. If there is a current, the current adds its own displacement to yours silently, and the error accumulates every hour, and there is no way to detect it out of sight of land. Anson's squadron was fighting west, in the narrowest part of the Southern Ocean, against a current carrying more than 170 million cubic meters of water per second in exactly the direction they were trying to leave. By his reckoning, Anson had cleared the Horn and had put roughly 10 degrees of longitude between his ships and the Cape. 10 degrees at that latitude is a substantial margin, several hundred kilometers of open water, more than enough to justify turning north toward the Pacific and toward the fresh food that his dying crews needed. Turning north was not a gamble. Given his plot, it was the obvious, correct, professionally sound decision, and he was also under a form of pressure that no chart accounts for. Every extra day at sea was killing men. He hauled north. And there was land ahead, where by every calculation available to him, there was open ocean. The east-setting drift had been pushing the squadron backward the entire time. Not violently, not visibly, just continuously, hour after hour, week after week, subtracting from every mile they thought they had gained. They were nowhere near where they believed they were. They were still against the coast of Tierra del Fuego, and had they made that turn at night, or in the fog that regularly forms in that area, several ships would have been on the rocks before anyone saw anything. They came about and started beating west again, and the ships that had almost nothing left had to do all of it a second time. That is the moment the Antarctic Circumpolar Current announced itself to European navigation, more than 2 centuries before anyone measured it. Not as a discovery, as an unexplained, repeatable, potentially fatal error in position, showing up in the logs of ships that were doing everything correctly. The squadron came apart under the strain. On the night of the 10th of April, in thick weather, Severn and Pearl lost contact with the rest. Their officers, with crews in the same condition as everyone else's, and no realistic prospect of forcing their way west, made the decision to give up the rounding and return east to the Atlantic and eventually to Brazil. The captain of the Pearl reportedly regarded the decision as a disgrace to him personally. Read that carefully, because it is the sharpest available evidence about the pressure these men were under. Turning back to save the surviving crews was so professionally shameful that a naval officer recorded it as a stain on his name. The Wager did not have that option. She was a converted merchantman carrying the expedition's heavy ordnance and stores, slower and less weatherly than the warships, and she was in poor condition. Separated from the squadron, damaged, with her captain incapacitated by a fall, she worked north up the Chilean coast in exactly the situation Anson had nearly put the whole squadron into. A ship uncertain of her longitude, closing an unlit, uncharted mountainous coast in bad weather. At around 4:30 in the morning on the 14th of May, 1741, she struck. Of roughly 250 men aboard, about 140 made it ashore onto a bleak island in the Guayaneco archipelago that is now called Wager Island. What happened afterward became one of the most notorious episodes in Royal Navy history because the survivors split into factions, discipline collapsed, a man was shot dead by the captain, and the group fractured into separate parties that attempted separate escapes. A handful eventually reached Britain by different routes and years apart, and the resulting court proceedings had to grapple with a question the Articles of War had never properly addressed: whether naval authority survives the loss of the ship it was attached to. Anson kept going. The Centurion worked north, made Juan Fernandez, and by then, the arithmetic of the voyage had turned into something almost unreadable. She had left England with a full complement and arrived with a fraction of it, and the men who had died mostly of a disease that fresh vegetables would have prevented. The squadron never reassembled. The trial was eventually scuttled. The Gloucester, rotten and unmanageable, was burned. Anson pressed on across the Pacific with the Centurion alone, took the Manila galleon Nuestra Señora de Covadonga off the Philippines in June 1743 with a crew that had been rebuilt from survivors, and came home in June 1744 with a treasure so large it was paraded through London in wagons. Of roughly 1,900 men who sailed, over 1,300 died. The overwhelming majority were killed by scurvy, not by drowning. Anson returned a national hero, and the voyage produced an authorized account, compiled by the chaplain Richard Walter and published in 1748, which became a bestseller and stayed in print for generations. Strip away the treasure and the celebration, and look at what that voyage actually proved. It proved that in the Drake Passage, Benditas Chicken, Dimitrothi, the water moves the ship in a direction the ship cannot detect, and that this error is largest exactly where the consequences are worst, near an unlit coast, in poor visibility, with a crew too sick to handle an emergency. It proved that the deadliest thing about the passage in the age of sail was not the sea state at all. It was time. The passage held ships in place, and the longer it held them, the more the slow killers aboard had to work with. And it proved something less comfortable about decision-making. Anson did not make a bad call. He made the right call based on the best information any navigator on Earth could have produced in 1741. The information was wrong for a reason nobody had a name for yet. So the obvious fix was better information. Know where you are, and the trap closes. That fix arrived. In 1761 and 1762, John Harrison's fourth timekeeper went to sea and kept time well enough to determine longitude, and within a few decades, marine chronometers were standard equipment. Charts improved. The coast got surveyed properly, including by the Beagle under Robert Fitzroy in the 1820s and 1830s, which is why Darwin was in these channels at all. Steam engines arrived, and a steamer does not have to beat against the wind for 6 weeks, because it simply drives through it. Every single one of those problems got solved. And then, in the winter of 1916, 22 men were living under 2 upturned boats on a beach in the South Shetlands, and none of it helped them at all. The short version of how they got there is well known and is not the interesting part. Ernest Shackleton's Imperial Transantarctic Expedition sailed in 1914, intending to cross the continent on foot. The ship, Endurance, was beset by pack ice in the Weddell Sea in January 1915 before anyone had set foot on the continent, drifted with the ice for 10 months while the pressure worked on her hull, and was crushed. She sank on the 21st of November, 1915. 28 men camped on moving ice for another 5 months, and when the floe they were on broke up, they took to 3 small boats and made a landing on the 15th of April, 1916, at Cape Valentine on Elephant Island, at the northeastern end of the South Shetlands. Falling rock made that first beach untenable, and 2 days later they shifted the camp about 7 miles west to a narrow gravel spit that came to be called Point Wild. Elephant Island is not a refuge. It is a lump of rock and glacier with essentially no shelter, no vegetation, no food source beyond what can be killed on the beach, and no possibility whatsoever of anyone finding you there by accident, because nothing goes there. The men were the first humans known to have spent any real time on it. So Shackleton took 5 men, and the strongest of the 3 boats, the 22.5-foot James Caird, and sailed for South Georgia on the 24th of April. That crossing, roughly 1,300 kilometers across the Scotia Sea in an open boat in the southern autumn, navigated by Frank Worsley with a sextant he could only use during the rare breaks in cloud, is one of the genuinely extraordinary feats of small boat seamanship on record. They made the coast of South Georgia on the 10th of May, on the wrong side of the island, and Shackleton, Worsley, and Tom Crean then walked over the unmapped interior to reach the whaling station at Stromness. The popular telling usually stops right there. Shackleton reaches help. Everyone is saved. Everyone was not saved. 22 men were still on a beach 800 kilometers away, on the far side of the water this entire story is about, and it was now winter. Understand what that meant operationally. Getting to Elephant Island from South America or South Georgia means crossing the Drake Passage region in the season when the pack ice extends furthest north. The pack does not sit still. It is driven by wind and current. It advances and retreats over days, and a route that is open on Monday can be shut by Thursday with no warning and no way to know from a distance. A ship that pushes into it and gets beset does not sink immediately. It simply stops being a ship and becomes another expedition needing rescue. Shackleton had no vessel, no money, and a world war going on, which meant every capable ice-strengthened ship and most competent crews were committed elsewhere. What he had was urgency, and the knowledge that the men on that beach were eating penguin and seal that would run out. He made 4 attempts. The first was the Southern Sky, a whaler borrowed at South Georgia, which sailed on the 23rd of May and got within about 100 kilometers of Elephant Island before running into pack ice that was solid across every approach. She was not ice-strengthened, and pushing further would have meant losing her. They turned back on the 31st. The second was the Instituto de Pesca Niguan, a Uruguayan government trawler from the 10th to the 16th of June. Same result. She reached the ice edge, found no way through, and had to withdraw before her coal ran too low to get home. The third was the Emma, a schooner out of Punta Arenas, from the 12th of July to the 8th of August, towed part of the way by a Chilean vessel. She got beaten back as well. 3 vessels, 3 failures, and each failure cost weeks, and each week made the situation on the beach worse, in ways nobody on the mainland could measure, because there was no communication of any kind. Nobody on Elephant Island knew whether Shackleton had reached South Georgia at all. Nobody in South America knew whether the men on Elephant Island were still alive. The information gap was total in both directions for over 4 months. Frank Wild, left in command on the island, dealt with that by running the camp as though relief were coming that day. He had the men keep their gear packed and a hoosh ready to eat at short notice, and every morning he told them to get ready. The boss might come today. Not optimism. A deliberate management decision to prevent a group of starving men from settling into the kind of passivity that kills people in survival situations. The 4th attempt was the Yelcho, and on paper the Yelcho was the worst-equipped vessel of the four. She was a small steam tug of the Chilean Navy. She had no radio. She had no proper heating system. She had no electric lighting. She had no double hull and no ice strengthening of any kind. Putting a vessel like that into Antarctic pack ice in August is, by any normal reading of seamanship, indefensible. Ice does not need to hit hard to open a plate on a thin single-hulled steel tug, and if she was holed at that latitude in winter, nobody was coming for her either. Her commander was Luis Alberto Pardo Villalon, and the crew that went with him were volunteers. She sailed from Punta Arenas on the 25th of August, 1916, and crossed north to south through exactly the water Anson's squadron had been unable to beat through in winter, in a boat you would not want to take, across a large lake. And here is where the physical environment gives something back, which almost never happens in this story. Somewhere around 55 degrees south, ships cross what oceanographers call the Antarctic Polar Front, and everyone else calls the Antarctic Convergence. It is the boundary where cold, dense Antarctic surface water sinks beneath the warmer, sub-Antarctic water flowing down from the north. It is not a line on a chart so much as a moving band, typically a few tens of kilometers wide, and you can feel it. The sea surface temperature drops, often by around 3 degrees Celsius over a very short distance, and in winter the contrast can be considerably larger. Warm, moist air sitting over suddenly much colder water does the obvious thing. It condenses. Fog forms along the front, and it can be thick enough to reduce visibility to a few hundred meters or less. Fog is normally the thing that kills you in an ice-strewn sea because you cannot see growlers and bergy bits until they are alongside. And a growler is a piece of very hard glacial ice riding low in the water with most of its mass invisible. For the Yelcho, the same conditions that made the approach blind also came with the calm, and Pardo used it. The pack ice, which had beaten 3 previous ships, had opened. He pushed in without radar, without a searchlight, without ice strengthening, in a fog, and by one account judged his distance from the ice and the land by listening to the echo of his own ship's siren coming back at him. No manual contains that technique. It is a man using the only sensor he has. On the 30th of August, 1916, the Yelcho came into sight of Point Wild. The men on the beach saw the ship and got their gear. The transfer took roughly an hour because Pardo would not risk the tug close into that shore for any longer than he had to, and there was no guarantee the ice would stay open. All 22 men came off. Nobody was left. Nobody was lost during the evacuation, and Shackleton counted them on the way past. The Yelcho returned to Punta Arenas on the 3rd of September to a reception from the entire city. Now sit with the thing that is genuinely strange about this. 4 vessels tried. The 3 that failed included a purpose-built whaler and a government trawler, ships designed and manned for hard southern work. The one that succeeded was an unheated, unlit, single-hulled harbor tug with no radio. The Yelcho did not succeed because she was better. She succeeded because she arrived in a 5-day window when the ice had opened, and because her commander was willing to go into it. So the passage teaches a second lesson, and it contradicts almost everything the modern world believes about safety. In this environment, equipment sets your ceiling, timing decides whether you live. A well-found ship arriving during a closed window fails. A poor ship arriving during an open window succeeds. And the window is not something you can create, buy, or schedule. You can only wait for it, recognize it, and be positioned to use it, which is exactly the capability that gets destroyed the moment somebody else is paying for your time. The Yagan could wait. Pardo, remarkably, was allowed to wait because the Chilean Navy let him try when the moment came rather than ordering him out on a date. Almost nobody else in the history of this water has had that freedom. And the reason is that the Drake Passage sits directly across the routes to things people badly want. Start with the first of those things because the way it opened is genuinely grim. In 1819, Spain was losing South America. Independence movements were winning across the continent, and Madrid was pushing reinforcements to the Pacific coast to hold what was left. On the 2nd of September, 1819, a Spanish squadron was working south of Cape Horn, bound for Callao in Peru. The flagship was the San Telmo, a 74-gun ship of the line launched in 1788 under Captain Joaquín de Toledo y Parra, with Brigadier Rosendo Porlier y Asteguieta commanding the squadron. Aboard her were 644 officers, soldiers, and seamen. She was doing what warships did in that water, driving west and south in bad weather, in company. Then a wave took her tiller. That is the whole mechanism, and it deserves a moment. The tiller is the lever on the rudder head. Lose it, and the rudder is free, which means the ship cannot be steered. In moderate conditions, that is a serious but survivable problem. A competent crew can rig a relieving tackle to the rudder head or steer with sails alone by balancing the rig, and ships did both regularly. Both solutions require sea room, time, and conditions in which men can work on an exposed deck. She had none of those. In a heavy following sea, a ship that cannot be steered sloughs sideways into the trough, and once she is beam on to breaking crests, she rolls, takes water aboard, and the problem compounds itself with every wave. Another vessel in the squadron saw the San Telmo's condition and could do nothing about it. There was no way to pass a line, no way to take men off, no way to tow. She was watched, and then she was not there. All 644 were lost. No survivors, no wreck site, no formal inquiry of the kind that would exist today. The story does not end there, and this is the part that connects it to everything that follows. Earlier that same year, in February 1819, an English merchant captain named William Smith, working the brig William south of Cape Horn, had been driven far enough down to sight land nobody had charted, the South Shetland Islands. He returned later in the year and landed, and when sealers began arriving in that archipelago, wreckage and remains were reportedly found on the shore of Livingston Island. The identification has never been conclusively proven, and it should not be presented as certain. What is on the record is timing and location consistent with the San Telmo, and the resulting claim, widely repeated in Spanish and Chilean sources, that her crew were the first human beings to die in Antarctica, arriving as debris. Now hold those two events side by side because they happened within months of each other, and they defined the next 2 centuries. A ship full of men was destroyed crossing this water, and a captain found islands full of fur seals just beyond it. The sealing rush that followed was one of the fastest and most complete resource extractions in maritime history. Word of the South Shetlands got out, and within a couple of seasons, dozens of vessels from Britain and the United States were working the beaches. Fur seal pelts were worth serious money in the China trade, and the animals had never encountered humans, which meant they did not run. Crews were landed on beaches with clubs and knives, left there for weeks with minimal supplies, and picked up later with the skins. Within roughly 5 or 6 years, the fur seal population of the South Shetlands had been reduced to commercial extinction, and the industry moved on. Consider what that did to the decision-making. A sealing gang landed on an island in the South Shetlands had no ship, no shelter beyond what they built, and no ability to leave. Their survival was entirely dependent on a captain coming back for them across the Drake Passage, Weisseisten or Hazard Jamichel, on a schedule set by his cargo and his competitors, rather than by the weather. Ships were lost in that trade and men were left behind, and the record of it is thin because sealing captains had commercial reasons to conceal where they were working and what happened there, and the pattern takes its permanent shape right here. The Drake Passage stopped being a barrier to be survived and became a toll on a route to something profitable, and the people paying that toll were increasingly not the people making the decision to cross. Whaling industrialized the same logic on a larger scale. Shore stations went in at South Georgia from 1904 and later in the South Shetlands, and then factory ships arrived that could process whales at sea and did not need a harbor at all. Whaling was a seasonal business with a hard economic clock. You went south when the ice allowed, you worked until you could not, and you came back. Companies had capital tied up in ships and stations that only earned during a window, which meant pressure to arrive early and leave late. At exactly the edges of the season, when ice and weather are least predictable. The whalers also produced something valuable and unintended. They were the only people who were down there year after year, and their observations, their logs, and their knowledge of local conditions were what expeditions relied on. Shackleton went to Stromness because whalers were the nearest functioning human infrastructure in the Southern Ocean, and it was whalers who gave him the first ship for the first relief attempt. Then the whales ran out too. The stations closed, and for a couple of decades the Southern Ocean went quiet except for scientific stations and the vessels supplying them. And then somebody had a genuinely new idea: sell the crossing itself. In January 1966, a Swedish-American travel operator named Lars-Erik Lindblad chartered an Argentine vessel, the Lapitaya, and took 57 paying passengers to Antarctica. Not scientists, not crew, tourists. It had never been done as a commercial product before, and it worked. In 1969, he went further and had a small ship built specifically for the job, a red-hulled vessel of about 100 berths designed to carry passengers into ice-strewn coastal water and put them ashore in small boats. She was called the Lindblad Explorer. Remember her? The industry Lindblad started grew slowly at first, and then did not. The International Association of Antarctica Tour Operators was founded in 1991, partly to write standards for an activity that had no rules, and its records give a clean measurement of what happened next. In the 1992 to 1993 season, 6,704 tourists made landings in Antarctica, carried by 10 operators using 12 ships across 59 voyages. That is the entire industry 30-odd years ago. In the 2022 to 2023 season, 104,897 people traveled to Antarctica with AITO operators. 50 operators, 60 vessels, somewhere around 540 voyages. Roughly 15 times the number of visitors compared to when the records began. The great majority of those people go to the Antarctic Peninsula, and the great majority of those depart from Ushuaia, at the bottom of Argentina, which means the great majority of them cross the Drake Passage. Twice. Out and back. Roughly 48 hours each way if the ship makes reasonable speed. A mass market transit, in other words. 2 days of open Southern Ocean in both directions, sold as the price of admission to the ice. The industry has a nickname for the two possible outcomes, and it tells you everything about how the risk is understood. If the crossing is calm, they call it the Drake Lake. If it is not, they call it the Drake Shake. The framing is a coin flip, something that happens to you. Whether as a lottery ticket rather than as a system you are inside. Now think about the schedule underneath that. An expedition voyage is sold as a fixed product with a fixed date. Passengers fly internationally to Buenos Aires or Santiago, then onward to Ushuaia on non-refundable tickets to join a ship on a specific afternoon. The ship has to be back on a specific morning because the next 150 passengers are already in the air. The vessel is chartered or owned at a daily cost that runs into 6 figures. Crew are contracted. Fuel is bunkered for a planned route. The permits, the landing site allocations coordinated between operators, and the return flights are all locked to the calendar. None of that flexes for weather. A master leaving Ushuaia can adjust his timing by hours. He can leave a little early to get ahead of a system, or hold in the Beagle Channel for part of a day, or alter his track east or west to take a low-pressure system on a better angle. And good masters do all of these things constantly. What he cannot do is what the Yagan did, and what Pardo was permitted to do, and what every sealing captain wished he could do. He cannot decide that this week is a bad week and go next week instead. So the fundamental structure of the modern crossing is this: a fixed departure into a variable environment repeated 540 times a season, across the one stretch of water where the wave field is set by mechanisms the forecast cannot resolve. And the ships are genuinely very good. This is not a story about corner cutting. Modern expedition vessels are built to ice classes. They have stabilizers, redundant propulsion, satellite communications, ice radar, and masters with polar experience. Purpose-built polar tonnage, delivered in the last decade, is dramatically more capable than anything Lindblad had. The Polar Code, which entered into force in 2017, imposed mandatory requirements on ship design, equipment, crew training, and voyage planning for polar waters. That capability is real, and it created something that will run through the rest of this story. Better ships did not make the passage safer in the simple sense. They made it crossable by far more people, far more often, and the total number of human beings exposed to it went up by a factor of 15, which brings the story back to that little red ship. The Lindblad Explorer went through several owners and names over 4 decades. By 2007, she was operating as the MS Explorer under the Liberian flag on the Peninsula Run, 38 years old, and still doing the work she had been designed for. Ice-strengthened, small, handy. A vessel with more Antarctic seasons behind her than most of the fleet. On the 23rd of November 2007, she was in the Bransfield Strait, the water between the South Shetland Islands and the Antarctic Peninsula, which is the sheltered side of the South Shetlands, and normally the reward you get after crossing the Drake. There were 154 people aboard, 100 passengers, and 54 crew. She was in ice at night, and she was making way. Here is the condition that matters and that almost no passenger understands. Not all ice is the same substance. Sea ice forms when the ocean surface freezes. First-year sea ice, the kind that dominates the Baltic and much of the Arctic in winter, is relatively young, relatively soft, full of brine pockets, and an ice-strengthened hull can push through it. Glacial ice is different. It began as compacted snow on land. It has been under pressure for a very long time. The air has been squeezed out of it, and it is dense, clear, and hard. A piece of glacial ice that has calved off a glacier or a berg and is floating low in the water is called a growler, and it is one of the few objects in the ocean that can open a ship's plating on contact. Growlers are also very difficult to detect. They ride low. They show almost nothing above the surface. They are dark and wet against a dark and wet sea, and radar returns from them are poor because there is so little of them above water to reflect. At night, in a seaway, with wave clutter on the radar screen, a growler is effectively invisible until the moment the lookout sees it, which may be too late to do anything at all. The master of the Explorer was Bengt Wyman, aged 49, and he was an experienced ice navigator. The Liberian investigation published in 2009 was specific about the nature of that experience. It was Baltic experience. He had handled a great deal of first-year sea ice, in a career's worth of it, and he was reading the ice around him in the Bransfield Strait as though it were the same material. It was not. The investigation concluded that the ice he entered was much harder land-derived ice, that he had underestimated it, and that he had not reduced speed at night in conditions of poor visibility. At around midnight, the ship struck. The damage was not spectacular. Understand that part first. The investigation established a breach on the starboard side, and the principal gash measured roughly 10 inches by 4, 25 centimeters by 10. A hole you could put both hands through in a ship 100 meters long. That should not sink anything. A hull is divided into watertight compartments, precisely so that a single breach floods one space and stops there, and the ship stays up while the crew deals with it. The Explorer had pumps. She had a crew who knew her, and the sea state was mild, three things turned a manageable breach into a total loss, and none of them were dramatic. The damage extended into a deep tank, which meant the flooding path was not confined to the space where the hole was. One of the ship's watertight doors failed, which meant a boundary that was supposed to hold water on one side of it did not. And the ship had down-flooding scuppers, drainage openings that once water was moving where it should not be, channeled it into the machinery spaces rather than away from them. The pumps ran and lost. That is the whole progression. Water arriving through a small hole, finding routes the design had not anticipated, reaching spaces that contained the machinery keeping the ship alive, and rising faster than the capacity to remove it. The first distress call went out in the small hours. The master ordered abandoned ship roughly 90 minutes later, and 154 people went over the side into 8 semi-rigid boats and 4 life rafts. Those boats were open. That detail is worth holding on to, because it is the difference between an inconvenience and a mass casualty event. An open boat in the Bransfield Strait in November means sitting in air near freezing, in spray, in wind, on water that is around 0 degrees Celsius, with whatever clothing you managed to put on when the alarm went. Hypothermia in that environment is not a slow process. Immersion is worse. Someone going into that water without a survival suit has functional use of their hands for a matter of minutes. Nobody went in. The evacuation was orderly, the boats were launched properly, and the passengers were kept in them. They were in those boats for hours. The response was coordinated through the Maritime Rescue System, and what actually saved them was the fact that other ships were in the region, and that the region has an unofficial mutual aid culture built by the operators themselves. The Norwegian vessel Nord-Norge, a Hurtigruten ship, altered course and came for them. She took every one of them aboard. They were taken to King George Island and then flown out through Punta Arenas. The Explorer stayed afloat, down by the bow enlisting for most of that day, and sank in the evening in roughly 1,300 meters of water. The little red ship that invented Antarctic tourism ended 38 years of work on the bottom of the Bransfield Strait. 0 deaths. 154 out of 154. By any measure, that is a successful outcome, and the Liberian investigation said so, commending the master and crew for an evacuation that was well ordered and undoubtedly saved lives. The same report recommended administrative action against the master's certificate of competency, on the grounds that a gap in his knowledge had caused the casualty in the first place. Both things are in the same document, and both are correct. Now here is the detail that turns this from a good news story into something that should make you uncomfortable. Those people were lifted out of open boats approximately 2 hours before gale force winds arrived in the area. 2 hours. Change one variable, and the entire outcome inverts. If the ice strike happens 2 hours later in the night, if the pumps hold 30 minutes longer and the abandoned ship order is delayed, if the Nord-Norge is 150 kilometers further away, if the master had decided to fight the flooding for another hour rather than get his people off early, any one of those and 154 people in open boats meet a gale in the Southern Ocean, and there is no version of that story that ends with everyone alive. The Explorer is held up correctly as an example of a well-executed evacuation. It is also an example of an outcome that depended on a weather margin of about 120 minutes, and nobody involved had any control over that margin. Modern polar operations run on that, and rarely say it out loud. The safety case is not only the ship, the training, and the procedures. The safety case includes the assumption that if something goes wrong, the weather will hold long enough for somebody to reach you. And now ask the obvious question: what if nobody is close? Because the Nord-Norge being nearby was not a system. It was a coincidence that the industry has since institutionalized as best it can, but it remains a coincidence at heart. Ships cluster on the peninsula in the season which is why help was available. The Drake Passage itself, the 2 days of open water on either side of that concentration, is not clustered. It is a crossing where ships pass out of sight of one another all season long. To understand what that means, look at the area one country is responsible for. Chile's search and rescue region, coordinated through the Chilean Navy, covers on the order of 26.5 million square kilometers, roughly 5% of the surface of the planet and about 35 times the land area of Chile itself. The region extends south from the Chilean coast through the Drake Passage, across the Antarctic Peninsula, and all the way to the South Pole. It is administered largely from the far south, with the Maritime Rescue Coordination Center and the Magallanes Maritime Governorate at Punta Arenas as the operational hub for the Antarctic sector. Chile is one of 5 countries carrying formal search and rescue responsibility inside the Antarctic Treaty Area, along with Argentina, Australia, New Zealand, and South Africa. Between them, 5 nations are nominally responsible for the entire Southern Ocean. None of that is a criticism of any of them. Chile's Coordination Center received an IMO commendation in 2008 for the multinational response to the Explorer sinking, and the Chilean Navy's record in that water is long and hard-earned. It is a statement about arithmetic. There is no configuration of ships and aircraft that provides meaningful coverage of 26 million square kilometers of subpolar ocean. What exists is a coordination capability, a legal duty, and whoever happens to be in the neighborhood, which is exactly the situation the Clelia the Saturn found herself in on the 7th of December 2010, when help was already alongside, and it made almost no difference at all. The Clelia de Sao Baki no Mustabaway Tidu was a small ship, about 90 meters, carrying 88 passengers and 77 crew, and she was doing the least eventful thing an Antarctic vessel does. She had finished a 10-day cruise of the peninsula. Everyone had seen what they came to see. She was northbound across the Drake Passage, headed for Ushuaia, on the last leg. The conditions were reported differently by different sources, which is normal and worth stating plainly rather than picking the most dramatic figure. Accounts describe sustained winds in the range of roughly 50 knots and seas somewhere between about 7 and 9 meters. Serious weather. Not extraordinary weather for that water in December. Nothing about the day would have prompted anyone to say that the ship was in danger. At around 20 to 11 in the morning in daylight, a single wave hit her. It broke against the bridge, which sits high in the superstructure, several decks above the waterline. It broke the starboard bridge window. Everything that followed came from that one opening. Water came into the bridge, which is the compartment containing the ship's navigation and control systems, and it went into the electrical circuitry. The communication systems went down, the radar was affected, and the engine control was affected badly enough that the ship lost the use of one of her engines. Follow what that combination does. A ship in a heavy sea keeps herself safe primarily by heading. She takes the seas on the bow or slightly off it, because that is the attitude in which she rides best, and in which breaking crests do the least damage. Holding that heading in 50 knots of wind requires power and steerage. Lose an engine, and you lose the ability to hold your bow up into the weather with authority, and a vessel that cannot hold her heading will come round into the trough, beam on, which is precisely the attitude that rolls ships. That is the San Telmo's problem in 2010, on a ship with satellite communications and stabilizers. Different century, different technology, identical physics, control surfaces, and propulsion versus a sea that will put you sideways the moment you cannot resist it. Lose the communications at the same time, and you also lose the ability to explain your situation to anyone. The Clelia de Serre. Tefuinus got a radio call out before or during the degradation, and the ship that answered was the National Geographic Explorer, a Lindblad vessel operating in the same area. She came, and she stayed. And now the moment that should permanently change how anyone thinks about rescue at sea. The National Geographic Explorer was there, alongside. Close enough that her crew filmed the Clelia de Sun Escoforu de Toyoin from the bridge wing, footage that later went around the world, showing a white ship burying her bow, rolling, disappearing into troughs deep enough to take her out of the frame entirely. 2 ships, in visual contact, one of them functioning perfectly. She could not take a single person off. There is no mechanism for it. You cannot launch a lifeboat from a rolling ship into 8-meter seas. The boat will be smashed against the hull during launch or swamped after it. You cannot bring 2 ships alongside each other in that seaway, because they will roll into one another, and the impact will hold them both. You cannot use a helicopter, because there is no helicopter with the range to reach the center of that passage, hover in 50 knots of wind, and lift 165 people, and neither vessel had a flight deck. Personnel transfer at sea has a weather limit, and that limit had been crossed hours before anyone knew there was a problem. What the Explorer's crew could actually do was rig a line-throwing device and fire a line across the gap between the 2 ships, with satellite phones attached, so that the Clelia II could talk to somebody. That is what rescue looked like on the 7th of December 2010, in the middle of the Drake Passage. A telephone, delivered by rope, across water, from one ship that was fine to another that was not. The Clelia Seku's crew got her under control. They kept her head to the weather with what they had, worked on the flooded electrics, and made way north at reduced speed with the Explorer escorting her the whole distance. She reached Ushuaia in the early hours of the 10th of December. 1 crew member was injured. No passengers were seriously hurt. Nobody died. And the incident is barely remembered outside the industry. It should be remembered because it demonstrated something no previous incident in this story had shown quite so cleanly. Anson's problem was that he did not know where he was. That got solved. Shackleton's problem was that nobody could communicate at all, and there was no ship able to reach the men. Communication got solved completely. A modern vessel in that position can be talking to a coordination center in Chile within seconds. The Explorer's problem in 2007 was that a hole in the hull outran the pumps, and she was saved by another ship being close enough. The Clelia II had everything. She had position to the meter, she had communications until the sea took them, and she got them back within hours by rope. She had a fully capable rescue vessel within sight for most of the ordeal, and the people aboard were exactly as unreachable as if they had been alone. This is the specific limit that technology has not moved, and probably cannot. Communication has become effectively instantaneous. Position has become effectively perfect. The physical act of moving a human body from one hull to another across broken water has not improved meaningfully in a century, because it is not an information problem. It is a problem of mass, motion, and the strength of the sea between 2 objects, and the Drake Passage generates exactly the sea state in which that transfer is impossible. Distress signals travel at the speed of light. Rescue travels at the speed of a ship in a gale, and it stops entirely at the last 50 meters, which is precisely the calculation that pushes people into the air. Because the obvious answer to a 2-day crossing of the world's most consistently violent stretch of open water is to stop crossing it on the surface. Fly. A jet or a turboprop covers the Drake Passage in about 2 hours instead of 48. It goes over the swell, over the eddy field, over the convergence, and lands on a gravel runway on King George Island where the ships take 2 days to arrive. Fly cruise itineraries built on exactly that logic are now a substantial part of the industry, sold specifically to people who do not want to face the crossing. The National Antarctic programs got there first, decades earlier, for the same reason. Supplying a research base by sea means committing a ship for weeks. Supplying it by air means a few hours. On the 9th of December 2019, a Chilean Air Force C-130 Hercules took off from Punta Arenas to make that 2-hour flight. The aircraft was a Lockheed C-130H Hercules, tail number 990, built in 1978, originally a United States Air Force airframe that had served with the Marine Corps as a tanker before Chile acquired it. The Hercules is one of the most successful transport aircraft ever built and has been flying in Antarctica since the 1960s. It can operate from rough strips, it carries heavy loads a long way, and it is famously forgiving. If you had to pick one aircraft type to run a supply route to a polar base, this is the one you would pick. The destination was Teniente Rodolfo Marsh Martin Airfield at Base Presidente Eduardo Frei Montalva on King George Island in the South Shetlands. Frei is the largest Chilean facility in Antarctica, effectively a small settlement. And Marsh is one of the very few places on the continent with a runway that a wheeled transport can use routinely. The mission was logistics, supplying the base, and inspecting a floating fuel supply line. There were 38 people aboard, 17 crew, and 21 passengers, and the passenger list is a fair description of what Antarctic operations actually consist of. 15 were Air Force personnel, 3 were soldiers, 2 were civilian engineers, 1 was a university student. The aircraft lifted off from Punta Arenas at 16:55 local time, which is 19:55 by the clock the controllers were using. Radio contact held for 1 hour and 18 minutes. At 21:13 UTC it stopped, then nothing. To understand what that gap means, look at the route. Punta Arenas to King George Island is roughly 1,000 kilometers, and almost all of it is over the Drake Passage. There is no alternate airfield. There is nothing underneath the aircraft for the great majority of the flight except the water this entire story is about. Polar aviation deals with that through a concept every Antarctic crew works with, the point of safe return, sometimes called the boomerang point. Beyond a certain distance, an aircraft no longer has the fuel to turn around and go back to its departure field, which means the decision to continue has to be made with an accurate forecast for a destination that may be an hour or more ahead, and where the weather can change faster than the aircraft can arrive. That is a very different kind of trap from the one that caught Anson, and it is the same trap. There is a moment in the middle of the passage, Winsmectiki success of Monakas, when one option disappears permanently. From that point on, the only remaining choice is forward, and there is no third option, because the water below is not survivable. Sea surface temperature in the Drake Passage runs from roughly 2 to 6 degrees Celsius, depending on latitude and season. A person in that water without an immersion suit loses effective use of their hands within minutes, and consciousness inside an hour, often much less. A controlled ditching in 8-meter seas is not a survivable event for a large transport aircraft in any realistic sense. There is no scenario in which help arrives soon enough. The Chilean Air Force reported that no emergency was declared. The search that followed was one of the largest ever mounted in that region, and it was genuinely multinational. Chilean, Argentine, Brazilian, Uruguayan, British, and United States assets were involved. A U.S. Navy P-8A Poseidon, an aircraft designed to find submarines and therefore extremely good at scanning open ocean, was committed. Chilean F-16s flew search patterns. Naval vessels worked the area. Israeli Defense Forces satellite imagery analysts were asked to assist. That is the modern rescue apparatus, at full stretch, with every technological advantage that did not exist in 1741 or 1916 or 2007. It was hampered by rough seas and poor visibility, which is what the Drake Passage does to search operations. A search aircraft looking for debris or survivors on that surface is looking for something small and dark in a field of moving whitecaps, under low cloud with the light going. Radar returns from small floating objects in a heavy sea are poor for exactly the same reason growler returns are poor. And a surface vessel searching in 8-meter seas has a horizon that appears and disappears with every wave. Debris was found about 31 kilometers from the last known position. On the 12th of December, 3 days after the aircraft went missing, The main crash site was located, roughly 27 kilometers from the last radar contact. Fuselage sections and major components were identified. Human remains were recovered, and identification work followed. All 38 people aboard were lost. The cause has never been determined. The official position is that the investigation was limited by an insufficient quantity of recovered components. What the evidence establishes is that the aircraft broke up completely, either in flight or on impact with the water, and that the sea in that part of the passage is deep enough that recovering the rest of it was never a realistic proposition. This is where a certain kind of documentary would start speculating. It is not going to happen here because the honest answer is that nobody knows. And the reason nobody knows is itself the point. An aircraft goes down in most parts of the world, and it is found. The wreckage is recovered. The flight recorders are read. The sequence is reconstructed. A report is written, and something gets changed so it does not happen again. That process is the reason commercial aviation is as safe as it is, and it depends entirely on being able to physically retrieve the aircraft. Over the Drake Passage, that chain breaks at the first link. The wreckage is under thousands of meters of the most turbulent water on the planet, in a place where a recovery operation would itself be a major expedition. The people who would have to conduct it would be exposed to exactly the same conditions that took the aircraft. So the loss of tail number 9990 proved something the sea incidents had not. Every previous escalation in this story was answered by a technology that removed one constraint. Chronometers removed positional uncertainty. Steam and diesel removed the dependence on wind. Radio removed the communication gap. Satellites removed it entirely. Aviation was the last one available, and it is the most complete. It removes the sea itself, replacing 48 hours of exposure with 2, and it removes it only while everything works. The moment anything goes wrong out there over open water, the aircraft is in a worse position than a ship would be, because a ship in trouble is still a ship. It floats, it holds people out of the water, it stays in one place. It can be found and stood beside even when nobody can be taken off it. The Clelia II was crippled, and her people were never in immediate danger of dying. The aircraft has no such state. It is either flying or it is in the water. And in the Drake Passage, the water is not a place where anyone can survive long enough to be reached. Aviation did not defeat the passage. It compressed the exposure into 2 hours and made those 2 hours absolute, which leaves the ships and the belief, reasonable, expensively engineered, backed by decades of statistics, that a modern purpose-built expedition vessel with stabilizers, redundant propulsion, and a forecast on the bridge screen has finally reduced the crossing to a matter of comfort. On the 29th of November, 2022, that belief was tested by a single wave, and the investigation that followed said something about the Drake Passage that the industry had not put on paper before. The Viking Polaris was almost brand new. She had been delivered that year, one of a pair of purpose-built polar expedition ships, along with her sister, the Viking Octantis, designed from the keel up for exactly this route. Ice-strengthened hull, a hull form specifically shaped to handle heavy head seas, fin stabilizers, redundant propulsion, modern bridge systems, satellite weather routing, and a crew operating under the Polar Code. She was, on paper and in practice, one of the most capable vessels ever put into the Drake Passage tourist trade. She was also doing the same last leg as the Clelia de Ceros, that Kwiwifekund 12 years earlier, northbound from Antarctica to Ushuaia, southeast of Cape Horn, with the crossing nearly behind her. The time was around 20 to 11 at night on the 29th of November 2022. Passengers were in their staterooms. Some were asleep. The conditions were rough. They were not remarkable, and this is the single most important sentence in this entire account, so it is worth stating exactly as the investigators did. The Norwegian Safety Investigation Authority examined the sea state at the time of the accident and found that it was within the sea states defined in the wave scatter diagram the ship was designed for. Read that again? The sea was inside the design envelope. Whatever the ship was built to handle that night was not worse than it. A breaking wave struck her side, not a wave of legendary height, a wave whose crest had gone over, which is the mechanism from the beginning of this story. Swell, arriving in a compressed, current-sheared, topographically stirred sea, steepening past the angle at which a wave face can hold itself together, and coming down as a moving wall of water rather than a slope. The investigation found that the ship's course and speed, combined with that breaking wave, produced the impact. That is a neutral engineering statement and not an accusation. The relative angle and velocity between a hull and a breaking crest determines the pressure delivered, and no bridge team can steer around individual waves in the dark. 7 stateroom windows failed. Water and glass entered 7 occupied cabins on a ship in the middle of the Drake Passage at night. The damage inside those staterooms was described in the report as major. Sherry Xiaonong-ju, an American passenger aged 62, was struck by the shattering glass and died. Initial media reports put the number of injured at 4. The safety investigation recorded 8 people injured in addition to the fatality. The ship was not in danger, that is worth being clear about. She had no flooding of consequence, no loss of propulsion, no threat to her stability. She continued to Ushuaia and disembarked her passengers. And that is what makes the finding so unsettling, because there was no chain of failures to point at, no ice strike, no engine loss, no communications blackout, no navigational error, no storm outside the design case. A modern ship correctly operated, in weather she was built for, and a woman was killed in her cabin by a window. So the investigators went after the window. Their conclusion was that the windows were inadequately dimensioned for the load that hit them. And then they went a step further, into territory that is genuinely uncomfortable for the industry, and stated that the design pressure requirements and current regulations yield values too low to withstand the pressure loads produced by breaking waves. Not that this shipyard got it wrong, that the rules were wrong. Understand the distinction, because it is the whole reversal. A structural design standard for a ship's side windows has to specify a pressure the window must survive. Those pressures are historically derived from the hydrostatic and hydrodynamic loads associated with a given sea state. Essentially, how deep the water is over the panel and how fast it is moving. That calculation works well for green water and for non-breaking waves. A breaking crest is a different loading regime. It delivers a very high pressure spike over a very short time, from aerated water moving horizontally, and the peak of that spike is not well predicted by a wave height-based static calculation. Marine researchers have known this for a long time, and it is why breaking wave impact is studied as its own problem. The report's finding is that this understanding had not made it into the numbers the rules require. And then the NSIA said the thing that closes the loop on everything from the beginning of this story. Wind speeds capable of causing waves to break are common for much of the year. In the Drake Passage, common for much of the year. The word that was used everywhere in the coverage of this accident was rogue. A rogue wave hit a cruise ship. It is a satisfying word because it makes the sea the culprit and the event freakish, a statistical monster that came out of nowhere and could not have been anticipated. The investigation's finding points somewhere else entirely. The wave was not outside what that stretch of water routinely produces. The sea state was not outside what the ship was designed for. What was outside acceptable limits was the assumption written into the standard that told the designers how strong a window has to be. The sea was normal. The rules were not. The NSIA issued 3 safety recommendations to classification societies, to the Norwegian maritime authorities, and to the ship owner, regarding the strengthening of windows on the Viking Polaris and on her sister ship, the Viking Octantis. The windows on both vessels were reinforced. That is a real, specific, useful outcome, and it is also worth being precise about its limits. 2 ships were fixed. The finding that the underlying design pressure requirements are too low applies to a great deal more than 2 ships, and changing an international structural standard is a slow process involving classification societies and regulators across many flag states. There are 60-odd vessels working Antarctic tourism. They were built to various standards in various decades in various yards. Every one of them crosses the same water, in the same season, past the same ridge on the seafloor, through the same eddy field, which leaves exactly one thing standing between every one of those ships and the water underneath it, and it is not the hull. Every mitigation that has been layered onto this crossing over 3 centuries rests on one assumption, and once you see it, you cannot unsee it. The assumption is that somebody knows what the weather is going to do. Anson could not know, and it killed his squadron slowly. Shackleton could not know, and it cost 3 relief attempts and 4 months. Modern operations are built entirely on the premise that this problem has been solved. The master gets a forecast, the forecast is good, and he plans around it. Departure timing, route selection, speed, when to secure the ship for heavy weather, when to warn passengers to stay in their cabins. Every one of those decisions is a forecast decision. So how good is the forecast in the Drake Passage? The honest answer is more interesting than either the reassuring version or the alarmist one. Numerical weather prediction in the Southern Hemisphere used to be substantially worse than in the North. For an obvious reason, there was almost nothing down there to measure with. Weather models need observations to start from, and the Northern Hemisphere is covered in radiosonde stations, airports, buoys, and commercial aircraft feeding data into the system continuously. The Southern Ocean has essentially none of that. No land, almost no permanent stations, very few ships, and those that are there are concentrated in a couple of shipping routes and a short season. Satellites closed most of that gap. Scatterometers measure surface wind by reading the roughness of the sea from orbit. Altimeters measure wave height by timing a radar pulse to the surface and back. Sounders retrieve temperature and humidity profiles through the atmosphere. Once those data streams were assimilated properly, Southern Hemisphere forecast skill improved enormously and now runs close to Northern Hemisphere skill at the same lead times. A genuine and underappreciated achievement. So the forecast a master receives in Ushuaia is good. It will tell him, with reasonable reliability, where the low-pressure centers are, how deep they are going to get, and what the significant wave height field is going to look like over the next few days. Here is what it cannot tell him. It cannot tell him about the eddy he is going to pass through at 2 in the morning. Because operational forecast products do not resolve individual mesoscale ocean eddies with the precision needed to predict where a local countercurrent will meet an incoming swell train. Satellite altimetry maps the large-scale current field, and it is genuinely useful, but the interaction that steepens a wave happens at a scale and a time scale below what any routine product delivers to a bridge, and it cannot tell him about individual waves at all. A wave forecast predicts a sea state. Significant wave height, peak period, direction. That is a statistical description of a spectrum. It is not a list of the waves he will encounter, and it structurally cannot be, because the wave that killed a passenger on the Viking Polaris was not a different sea state. It was a member of the distribution the forecast correctly described. The forecast tells you what kind of ocean you are entering. It does not tell you which wave in that ocean is going to break against your hull at the wrong angle. That is the gap the whole system sits on, not a failure of meteorology, a limit of what a spectral description can contain. Add one more thing, which is what the Drake Passage does to weather systems in the first place. The Southern Ocean is one of the world's most active regions for explosive cyclogenesis. Low-pressure systems that deepen extraordinarily fast. By the meteorological threshold of roughly 24 hectopascals in 24 hours, adjusted for latitude. The reason is the same reason everything else here is extreme. A continuous storm track with no land to disrupt it, a very strong temperature gradient between the subantarctic and the polar air, and an ocean surface constantly feeding energy upward. A system in that environment can go from unremarkable to dangerous inside a day. And a ship halfway across the Drake Passage is, by definition, 24 hours from either shore. That is the arithmetic that has not changed since 1741 and cannot be changed by any technology currently imaginable. A correct forecast, delivered on time, with a full day of warning, arrives at a vessel that needs a full day to reach shelter in either direction. The warning and the escape take the same amount of time. There is no margin in the system, and there never has been, because the width of the passage and the speed of the storms happen to match. You can improve the forecast to perfection, and that number does not move. Now add what has been happening to the water itself over the last few decades, and be careful here, because this is where documentaries usually start exaggerating. In 2019, Ian Young and Agustinus Rybal published an analysis in Science using 33 years of satellite data, 31 satellites, roughly 4 billion observations, validated against more than 80 ocean buoys. They looked for trends in wind speed and wave height globally between 1985 and 2018. Mean conditions showed small increases. The extremes showed larger ones, and the largest increases anywhere on Earth were in the Southern Ocean. Extreme winds up by about 1.5 meters per second, roughly 8% over 30 years, and extreme waves up by about 30 centimeters, roughly 5%. 30 centimeters does not sound like much. The instinct is correct, and it needs qualifying in one specific direction. This is a 5% increase at the top end of the distribution, in the region that already had the highest extremes on the planet. And the relevant physical quantity is not height, but energy, which scales with the square of the wave height, and impact pressure from a breaking crest, which scales more steeply still. It also matters that the increase is concentrated in the extremes rather than the mean. The average crossing is not measurably worse. The worst crossings are. That is the tension the whole modern industry is sitting inside. The ships got better. The regulations got stricter. The forecast got sharper. The season got longer, and the traffic went up 15-fold. And the tail of the distribution, the specific part that the design standards by the NSIA's own finding were not calculating correctly, got heavier. None of which stops anyone from going, because the reasons to go are as solid as they have ever been, and because there is a persistent belief running through the entire history of this water that if you can just reach shelter, you are safe. There is a place in the South Shetlands that tests that belief better than anywhere else on Earth. Deception Island sits at the southwestern end of the South Shetlands, and from the outside it looks like a horseshoe of black rock and gray ice, which is what it is. What it also is a volcano whose crater has collapsed and flooded, which means the inside of the island is a natural harbor, a sheltered basin of deep water almost entirely enclosed by land, in a region where sheltered deep water essentially does not exist. There is one way in, a gap in the caldera wall about 400 meters across called Neptune's Bellows, with cliffs on either side and a submerged rock sitting in the middle of the entrance channel. A ship going in has to thread it, and the wind funnels through the gap and accelerates in exactly the way wind accelerates through any narrow passage between high ground, which is where the name came from. Get through it, and you are inside a caldera with flat black beaches, water warm enough in places that geothermal heat comes up through the sand, and complete protection from the Southern Ocean. For anyone working in that region, this was the single most valuable piece of geography south of Cape Horn. The whalers took it first. A shore station went into Whalers Bay in 1912, and for 2 decades Deception Island was an industrial site. Boilers, oil tanks, accommodation, a cemetery. The station shut in the early 1930s when the economics collapsed and factory ships made shore processing unnecessary. Then the national programs moved in. Britain established a base there in 1944. Argentina and Chile both put stations on the island as well, and by the 1960s, 3 countries had permanent facilities inside the same caldera, in the best harbor in the Antarctic Peninsula region. On the 4th of December 1967, the volcano erupted. The Chilean station, Pedro Aguirre Cerda, was destroyed. 16 men were there. They were evacuated, and the British withdrew from their base the following day. That is the whole event in one line, and the operational reality behind that line is worth spelling out. An eruption inside a caldera means the eruption is between you and the exit, or the exit is behind ashfall, or the harbor you sheltered in is full of floating pumice and the ship coming to get you has to enter through a 400-meter gap with a rock in it under those conditions. The evacuation worked. Everyone got off. The British came back a year later, reoccupying in December 1968. In February 1969, the volcano went again, and this time the destruction came in the form of mud flows. Meltwater and volcanic debris moving downhill together tore through the abandoned whaling station at Whalers Bay, and the remains are still there. The middle torn out of the station house, boilers rusting in the black sand, an aircraft hangar with its roof gone. The base was abandoned for good on the 23rd of February, 1969. Nobody was killed in either eruption. A genuinely good outcome, and it was not luck. It was rapid evacuation by ships that were in a position to respond, again with the Chilean Navy heavily involved. But look at what the island proves. The single best shelter in the region, the one place where a ship can be completely protected from the Southern Ocean, is the inside of an active volcano with one narrow entrance. 3 nations built on it anyway, because the harbor was worth it, and the harbor was worth it because everything outside the harbor is the Drake Passage and the Bransfield Strait. That is the pattern in its purest form. The thing that makes a place valuable and the thing that makes it dangerous are the same feature. And people take the trade because the alternative is worse. Deception Island is still visited. Ships still go in through Neptune's bellows, and passengers still walk on the beach at Whalers Bay among the ruins. The volcano is monitored, and it has shown unrest at various times since 1969. It is not extinct. It is between eruptions. And reaching shelter is not the same as being safe, which the Antarctic Peninsula demonstrated again 20 years later in the most complete way available. On the 28th of January, 1989, the Bahia Paraíso, an Argentine Navy transport, had just finished a visit to Palmer Station, the American research base on Anvers Island. She was carrying 234 crew and 81 passengers, because by the late 1980s, national supply vessels were also carrying tourists, and Palmer was a regular stop. She was leaving. She was inside Arthur Harbor, which is protected water about 3 kilometers from a manned scientific base, in the middle of the austral summer, in daylight. She ran onto rocks. The hull opened along a tear roughly 10 meters long. Every person aboard survived. All 315 of them got off, and they were taken in at Palmer Station, a small research facility that suddenly had to shelter and feed several times its own population until other vessels could come and take them north. Its own logistical event, and it worked only because the station was there. The ship did not survive. She rolled onto her side and stayed there, and out of her went most of what she was carrying: diesel, jet fuel, gasoline, lubricating oils, hydraulic fluid, compressed gas cylinders. Estimates put the spill at around 600,000 liters. The response was immediate and largely futile. Containment booms in that environment, at that temperature, against that much fuel from a vessel lying on her side, could not do much. The oil spread through Arthur Harbor and beyond. Scientific assessment in the months and years that followed documented contamination in the water, the sediments, the seaweed, the limpets, the bivalves, the bottom-feeding fish, and the birds within a radius of a couple of miles. And researchers recorded population drops among skuas, giant petrels, gulls, cormorants, and penguins in the period afterward. Palmer Station existed to study that ecosystem. The scientists spent the following season studying what a fuel spill does to it instead. Notice what that incident proves that none of the others did. Everybody lived, every single person. It is, by the metric this story has been using, the most successful outcome in the entire record. And it was still a disaster because in this environment, the vessel and the place are also casualties, and neither of them recovers on a human timescale. There is no salvage industry within thousands of kilometers. There is no infrastructure to remove a wreck. The Bahia Paraíso stayed where she fell for years before a partial removal operation was mounted, and the ecological consequences ran on long after the last passenger had flown home, which is the answer to a question that has been sitting under this entire story without being asked directly. Why does anybody keep doing this? The tourist answer is easy and slightly unsatisfying, because Antarctica is the last place on Earth that looks like nowhere else, and 100,000 people a year decide that 2 days of open Southern Ocean is an acceptable price. That is a real answer. It is also the answer that gets all the attention, and it describes the least exposed population in this water. Consider the arithmetic of exposure for a moment, because it is badly misunderstood. A passenger crosses the Drake Passage twice in their life, out and back, 2 transits, and then they go home and show people photographs of penguins. The expedition staff and the crew on that same ship cross it every voyage of the season. An 11-day peninsula itinerary run back-to-back through a 5-month season is something on the order of 25 to 30 round trips, which is 50 to 60 transits every year, for as many years as they keep the job. Deck officers, engineers, hotel staff, expedition guides, the people who launch the small boats and drive them. They are in that water an order of magnitude more than the people they are carrying. They are the ones on deck securing things when it gets bad, and nobody writes articles about them. Then there is a population that almost never appears in any of this at all. The Southern Ocean is fished. Patagonian toothfish, sold as Chilean sea bass, is taken by longliners working the waters around South Georgia, the South Sandwich Islands, and the sub-Antarctic shelves. Krill is taken by trawlers in the Scotia Sea and around the peninsula. These are regulated fisheries with observers and catch limits, and the vessels are modern, and the work is done by crews who are out there in months when no tourist ship exists anywhere south of Ushuaia. On the 22nd of July, 2024, deep in the southern winter, the longliner Argos, Georgia was working about 190 nautical miles east of Stanley in the Falklands. She was 6 years old, built in 2018, operating for an Anglo-Norwegian company with 27 people aboard. This is in the South Atlantic rather than the Drake Passage itself, and that distinction should be stated plainly. But it is the same wind belt, the same wave climate, and the same rescue geometry. She sprang a leak in heavy seas. The crew fought it, and then they could not. And around 4 in the afternoon, local time, they had to abandon her into waves reported at around 8 meters with the wind still on. Launching a life raft from a sinking vessel in that sea state is one of the hardest things anyone will ever be asked to do. A raft in the water beside a rolling hull is trying to be crushed against it or blown away from it, and the people going into it are climbing down a moving surface in survival suits with cold hands. They struggled with it, and the record shows why that matters. Of the 27 aboard, 14 survived, and 13 did not. The rescue came the following day. 13 of the survivors were taken from a life raft by the patrol vessel Lilibet, and another was recovered by a Falklands-flagged toothfish vessel, the Robin M. Lee, which also recovered one of the dead. Notice the structure of that rescue and compare it to 1916. A government vessel and another fishing boat arriving the next day taking people out of a raft. That is the same architecture as the Yelcho. Whoever is in the region going in as soon as conditions allow. There is no other architecture available. There never has been. The difference between the Argos Georgia and the Explorer is not the quality of the ships or the competence of the crews. It is July versus November, and the presence or absence of other vessels nearby. That is the thing the tourist season conceals. From roughly November to March, the peninsula has 60 ships working it, and if one gets in trouble, another can usually reach it. For the rest of the year, and across the Drake Passage itself even in season, that safety net thins out to almost nothing, and the people working out there in those months know it perfectly well. And then, at the other end of the spectrum entirely, there are the people who cross this water on purpose in the smallest possible object. In December 2019, 6 men rowed across the Drake Passage from Cape Horn to the Antarctic Peninsula in a 9-meter boat called the Ohana, with a support vessel in company in a little over 12 days. No sail, no engine. They rowed around the clock in 90-minute rotations because the boat had to keep moving to avoid being rolled. A rowing boat, in the water that stopped Anson's squadron, that beat 3 relief ships in 1916, that put a wave through the bridge of the Clélie de Sauge. It is easy to be dismissive about that. It is more useful to notice that it is the same impulse, stripped of every commercial and institutional justification, that has been sending people into this passage for 500 years. Spain sent the San Telmo because it needed to hold a continent. The sealers went because pelts were worth money. The whalers went because oil was worth money. The national programs go because the science matters. The tourists go because it is the most extraordinary place they will ever see. And 6 people rowed it because it had not been rowed. Take away every economic reason, and the traffic does not stop. Worth being honest about that because it means the exposure is not going to be regulated away, and the water they are all going into is changing in ways that do not simplify into a headline. On the 21st of February, 2023, Antarctic sea ice reached a minimum extent of 1.79 million square kilometers, the lowest in the 45-year satellite record, beating the previous record set the year before. A real measured, documented change, and not in dispute. What it means for the danger is genuinely more complicated than either the reassuring or the alarming version. Less sea ice does not mean less ice. The icebergs and growlers that open the Explorer's hull are glacial ice. They come off the continent, and their supply is not governed by how much of the sea surface froze last winter. What changes is where they drift, and how long they persist in open water. Less sea ice does mean less wave damping. Sea ice suppresses wave growth. It takes energy out of a swell field. Open water where there used to be ice is open water that swell can propagate across and grow in. That is a straightforward physical consequence, and it points in the direction of more wave exposure closer to the continent, not less. And less sea ice combined with better ships means a longer operating season, which means more voyages in the shoulder months at the edges of the year when conditions are least predictable and there are fewer other vessels around to help. Nobody should claim from this that the crossing has become more lethal. The safety record of Antarctic tourism over the last 2 decades, measured against the number of people carried, is remarkably good. And it is good because of the ships, the polar code, the coordination between operators, and a great deal of competent seamanship. What can be said is narrower and harder to argue with. The number of people exposed has gone up 15-fold. The extremes of the wave climate in this ocean have measurably increased. The design standard governing one specific point of failure has been found by a national investigation authority to be calculating the wrong load, and the physical constraint that has governed everything since 1741, that the passage is 1 day wide, and the storms in it deepen in 1 day, has not moved a centimeter. So here is the system in one chain with nothing left out. 30 million years ago, give or take a disputed margin, the land bridge between South America and Antarctica opened into a deep water gap. Water could finally circle the southern continent without touching anything, and the strongest wind belt on the planet had an unbroken ocean to push. The Antarctic circumpolar current started, and it isolated Antarctica from the world's warmth, and Antarctica froze. The ice that people cross this water to see exists because this water exists. That current now carries around 173 million cubic meters of water per second, a figure that the people who study it were underestimating by about 30% until an array of instruments sat on the seafloor for 4 years and told them so. All of it has to pass through a gap 800 kilometers wide, which is the narrowest point on its entire circuit around the planet. Squeezed, it accelerates and organizes into jets and fronts that meander and shed eddies. Dragged across the Shackleton Fracture Zone, a ridge standing thousands of meters off the abyssal floor directly athwart its path, it turns turbulent, mixing around 20 times more vigorously than in the open Pacific upstream. Above all of that, swell arrives that was built somewhere else. There is no land at these latitudes, so the fetch is the circumference of the Earth, and the swell reaching a ship in the passage is already fully grown and has nothing to do with the sky overhead. That swell runs into the eddy field. Where the local surface flow opposes it, the wave energy compresses, the wavelength shortens, the crest rises, and the face steepens past the angle at which it can hold together, and it breaks. A breaking crest is not a slope that lifts a ship. It is a mass of aerated water moving horizontally that delivers a pressure spike in a fraction of a second, and the load it applies is not well predicted by the wave height number on the bridge screen. The forecast will tell a master the sea state. It cannot tell him which wave, because significant wave height is a statistical description, and the wave that comes through the window is a member of the distribution, not an exception to it. Weather systems in this ocean deepen explosively, and the passage is 1 day wide, and the storms are 1 day deep. The warning and the escape take the same amount of time. That equality is not a design flaw anyone introduced. It is a coincidence of geography and atmospheric physics, and it has been true for every vessel that has ever crossed. Into that put people for reasons that have never once been frivolous. Silver and a war in 1741. Reinforcements for a collapsing empire in 1819. Sealskins, then whale oil, then science, then supply flights to bases, then 100,000 paying passengers a year, then fish in the winter, then 6 people in a rowing boat. Give them better equipment and watch what it actually does. The chronometer removed positional uncertainty, and the ships kept coming. The engine removed dependence on the wind, and the ships went further from shelter. Radio and then satellite removed the communication gap entirely, and the Clelia the Sab and the Kiwo the Kinkiwe that Kunu proved that a perfectly delivered distress call does not move a single human being from one hull to another. Aviation removed the sea itself, and tail number 990 proved that it removed it only while everything worked, and that when something failed, there was nothing beneath the aircraft at all. Every one of those technologies solved the problem it was built for. Not one of them touched the last 50 meters. That is the constraint that has never moved, and it is the reason this place is different from other dangerous water. In most of the world's ocean, the gap between a distress call and a rescue is a matter of hours, and the sea will usually let you complete the transfer. Here, the coordination centers are excellent. The legal responsibility is clearly assigned. And Chile alone holds a search and rescue region of roughly 26.5 million square kilometers, about 5% of the surface of the planet, which is a statement about how little coverage is physically possible, rather than how much. Now look at all 6 of those incidents again and notice what they share, because it is not what people assume. Anson turned north on a plot that any navigator alive would have drawn. Pardo went into pack ice in a harbor tug, because that was the only ship available and the window was open. Bengt Weeman read the ice the way 30 years of Baltic experience had taught him to read it. The Clelia de Sexis. Tolygins bridge team took a routine northbound leg in serious but ordinary weather. The C-130's crew flew a route their Air Force had flown for decades in an aircraft type that has worked in Antarctica since the 1960s. The Viking Polaris was inside her design envelope with her passengers in their cabins. Not one of those was recklessness. Every one of them was a defensible decision made with the best information available at the time. And in every case, the environment removed an option faster than anyone could replace it. And in every case, the distance to help was measured in a unit the situation did not allow. That is the actual mechanism. And it is worse than recklessness would be, because recklessness can be trained out, which leaves one thing that has genuinely changed. And it is not the one people expect. The passage has not become more dangerous in any way that shows up cleanly in the statistics. It has become more crowded. 15 times more people in ships that are far better, crossing water whose extremes have measurably increased, protected in part by a structural standard that a National Safety Investigation Authority has now stated in writing, produces values too low to withstand the pressure loads from breaking waves. Waves, it also stated, are common in the Drake Passage for much of the year. 2 ships had their windows reinforced after that finding. The finding itself applies to a great deal more than 2 ships, and international structural standards do not change quickly. So the situation right now is this. The mechanism that has been running since the gap opened is running. The traffic across it is at an all-time high and rising. The specific point of failure that killed a passenger in 2022 has been identified precisely, publicly, and by a competent authority. And the ships keep leaving on schedule, because that is what the schedule is for. Go and look at what a departure actually consists of, because it is the least dramatic thing in this entire story, and it is the only part of it that is happening today. Ushuaia, in the late afternoon, in season, has ships alongside the pier and more anchored off. The town sits under mountains that still hold snow in December, and the pier is a working one. Fuel, water, provisions, containers of food for 150 people for 11 days, and passengers filing up a gangway with duffel bags in the colors their operator sent them. The crew are not thinking about the Drake Passage as an idea. They are securing the ship. Zodiacs get lashed down on their cradles because a small boat that comes loose on a deck in a seaway becomes a 2-ton object with momentum. Shell doors are closed and dogged. Deck furniture comes inside or gets strapped. In the cabins, the stewards check that drawers latch and that anything on a shelf is on a shelf with a lip. In the galley, everything goes into the fiddles on the ranges and the racks in the stores, because a loose stock pot in a heavy roll will injure somebody. On the bridge, the officer of the watch works through the passage plan, the weather files, and the departure checklist. There is a printout, or a screen, showing the forecast for the crossing. Wind direction and speed. Significant wave height in meters. Swell period and direction. It is a good forecast, produced by models that took 30 years and thousands of satellite observations to get this reliable. And it is honest about what it knows. The lines come off. The ship comes off the pier and turns east into the Beagle Channel. The channel is the calm part, and it lasts a few hours. Mountains on both sides, glaciers hanging in the valleys, sea lions on the rocks, a lighthouse called Les Éclaireurs, sitting on a low island a few miles out with its red and white bands, which is the photograph almost every passenger takes on the way out. The water is flat. Dinner is served normally. People stand on the outer decks in the long southern evening light. Somewhere out toward the eastern end of the channel, the pilot goes off, and after that the ship is on her own. The motion arrives gradually, and then it is simply there. A long, slow lift and settle that was not present an hour earlier. That is the first swell of the passage, and it did not come from anything anyone on board can see. It was made by a storm days ago, and thousands of kilometers away, and it has crossed open ocean to arrive under this hull at this moment, and it will keep arriving all night whatever the sky does. The stabilizer fins go out. Passengers who have never used them take the tablets that were left in their cabins. The announcement goes out to keep one hand for the ship on stairs and in corridors, and the handrails start getting used properly instead of decoratively. By full dark, the ship is in it. Roughly 800 kilometers of open water ahead, with the Antarctic Circumpolar Current running east beneath the keel. The Shackleton Fracture Zone, standing up off the seafloor somewhere along the track, the eddy field, turning slowly in the dark, and the polar front waiting somewhere around 55 south, where the sea temperature will drop and the fog may come. The forecast says the crossing should be manageable. It probably will be. Most of them are, and the ships are good, and the officers are good, and this route is run 540 times a season by people who know exactly what they are doing. In the corridors, the stewards have already done their last round. Behind the cabin doors, the lights are going off one at a time, and behind each of those doors is a window facing the sea, sitting at a height above the waterline that somebody calculated using a standard. On a ship built in a yard that applied the rules correctly, in a passage where breaking waves are common for much of the year.